Hello everyone, my name is Juan David Apollo. Today I'm going to talk about a topic that comes from a research paper titled Quantum System Engineering and a Structured Approach to Accelerating the development of a Quantum Technology Industry. This paper introduces the idea of quantum system engineering, or QSE, as a way to move quantum technology out of the lab and into real world applications. We all know that quantum computing is one of the big goals in science today. The quantum technology is not just about computers, there are also quantum sensors, precision clocks, gravity detectors, secure communication systems, and even biomedical imaging tools, all based on quantum principles. These technologies could change entire industries like navigation, drug discovery, meteorology, and cybersecurity. But there's a challenge. Quantum systems are very fragile, complex, and hard to control. So, we need a new way to design and build them. And that's where quantum system engineering comes in. Now, what is system engineering in general? It's a process used to develop complex systems, like satellites, airplanes, or electronics. Be careful managing all parts of the design, from requirements to design, testing, maintenance, and end of life. It's used in industries like defense, space, and telecommunications. But quantum systems are not like traditional systems. Why? Because of quantum entanglement and non-locality in classical systems. We can separate components and test them independently. But in quantum systems, the parts are often entangled, meaning we can treat them separately. This creates two big problems mentioned in the paper: the modeling problem and the interface problem. The modeling problem is that quantum systems grow in complexity exponentially as we add more parts. This makes them very hard to simulate or predict. And the interface problem is about defining clear boundaries between subsystems, which is very difficult with quantum states that be isolated. This is a big challenge for traditional system engineering, which relies on clearly defined components. So, what are some of the key areas in quantum system engineering according to the paper? Number 1. Abstracting and high-level design. Quantum mechanics is abstract and hard to interpret. We need a new design tools that help people work with quantum systems even without the physics knowledge. Number 2. Design for reliability. Quantum states are very sensitive to noise, temperature, and external environments. We must understand how quantum devices can fail and how to protect them, especially when they interact with classical systems like power supplies and remote electronics. Number 3. Design for test and certification. In many cases, it's hard to test quantum devices because measuring them can change their state. We need methods to certify that quantum system works, especially for things we can't simulate using classical computers. Design number 4. Design for scalability. It's one thing to make quantum device work in a lab. It's another thing to make it big, stable, and useful in real-world conditions. That means building good interface between quantum and classical parts and designing systems that can grow. Number 5. Modeling and simulation. We need better computer tools to model and simulate quantum systems, especially when they interact with classical quantum. This is essential to accelerate development and remove the need for every engineer to be an expert in quantum theory. Number 6. Requirement and specification. In traditional engineering, we start with a system requirement specification, a document that defines what the product must do. But quantum systems need a new types of requirements that include quantum constraints, like keeping coherence, avoiding parasitic entanglement, and managing environment interactions. Number 7. Ontology. Finally, we need a shared vocabulary between physicists and engineers. Words like state, function, or spin can mean very different things depending on the discipline. Creating a common ontology helps teams work together and avoid misunderstandings. In conclusion, the paper argues that quantum system engineering is essential if we want to move quantum technologies out of the lab and into real life. It's not enough to build a cool prototype. We need to design systems that are reliable, scalable, and testable. This will help speed up the development of quantum tools that can improve medicine, communication, navigation, and more. Thank you for listening.